Good afternoon. I'm going to talk a little bit about mostly coastal modelling, a little bit of nod to inland, but mostly on the basis of you can't really model coasts without some kind of terrestrial input at some point. I suppose really in the context of this talk we're really talking about seascapes rather than landscapes, because I always find it a slightly confusing term as a marine scientist that they sort of impose landscapes upon us. So this is, I'm afraid I've drawn from a piece of PML corporate blurb really, but it's a rather nice diagram which shows a whole range of issues that you have to deal with here. You've got basic processes in the marine environment, you've got the phytoplankton growth, you've got the recycling of carbon and nutrients, you've got fisheries, and then you've got a whole bunch of human activity from offshore energy through to fishing, you've got aquaculture, then you've got stuff happening on the beach, you've got coastal tourism and recreation, and you've got stuff happening on the land which is influencing this, including land-derived sources of pollution, impact of urban environments, inputs into the atmosphere which then feed into the ocean, obviously the supply of nutrients and other contaminants, sediments down rivers, you've got risks of flooding, but you've got a whole range of challenges here which in terms of trying to understand the landscape and how it works. And all of this is sort of grist to the mill for numerical modelling. At the same time, we've also got to think of it as virtually everybody else has put up a similar slide to this now, as a socio-ecological system. Perhaps one of the interesting challenges here is that often we're looking at socio-ecological impacts, and the socio-ecological bits actually take place on the land, but the impacts on the environment are taking place on the water. So there's a sort of there's a bit of a decoupling there, in terms of where the processes take place, as opposed to looking at your urban or agricultural environments where people who are actually impacting on the environment in the marine environment are not always seeing directly what's going on, particularly if it's a little bit offshore or particularly if it's under the water. Right? People see what goes on in the near shore, but the impacts on the seabed, say of trawling or something, are completely hidden from people in the environment. Okay, but for that in itself, when we're thinking about landscapes and we're thinking about it as a socio-ecological system, we sort of have to think there's a challenge here to think about how we relate all these coastal community activities and what the impacts are on coastal societies and how we relate that to what's actually going on in the environment. And the sea, the marine environment provides a wide variety of ecosystem services, and we've been through, again, many ways very analogous to what the terrestrial ones. Language is slightly different, but we have a bunch of provisioning services, including food provision. We have regulating services, including, oxygen supply being a very important one, climate regulation, waste treatment, assimilation. Got habitats, particularly for migratory nursery habitats for fisheries, and then we have a whole raft of cultural services as well. And this then leads us, we have a whole range of questions then that we can start to think about. We've got an axis on one side of sort of biogeochemical processes, on the other side of ecological processes, and the kind of things we're then asking questions around are carbon sequestration, deoxygenation, ocean acidification, impacts of eutrophication, coastal erosion, things that impact leisure and recreation, including bathing water quality, the presence of charismatic species, fisheries and aquaculture. And in order to address these, we therefore need a model system that can describe a whole variety of things across the ecosystem, from plankton growth and the nutrients undercycling that, chemistry associated with it, macrophytes and seagrasses, the benthic, that's the seabed fauna, fish and fisheries, mammals and birds. So there's a complex system here to be modelled and addressed. And the other issue is, of course, we're not dealing with a static system, and we're dealing with a highly interconnected system. So we've got a whole bunch of model scales. And while at a coastal system we're sort of looking at, well, I guess it depends what your definition of coastal is. I know the statutory definition, I think, is 12 kilometres offshore. Of course, the sea is a highly dynamic environment and in itself doesn't necessarily recognise those statutory definitions. The organisms that live in the ocean certainly don't represent national boundaries or so forth. So really, we're looking at sort of coastal shelf seas areas and inshore into bays and estuaries. But we should also bear in mind that the whole global ocean is interconnected. So there's a strong connectivity between the global ocean driving shelf seas processes, driving coastal and estuarine processes. And at the same time, these are also strongly influenced, particularly in the near shore, by the input of rivers and catchments. And within the UK, there's a bunch of modelling tools, particularly the NEMO models that are used in order to describe the physics of these systems. So what does a marine system modelling system look like? This is the kind of thing we're working towards at the moment. We've got various representations of marine physics at different scales, from global to local. We have a biogeochemical ecosystem model, which describes both pelagic processes. This is plankton, grazing and fish. Plankton and grazing, zooplankton. Also the seabed, the benthic ecosystem processes. We can couple this to models of fish and fisheries. We can couple this to models of aquaculture growth. We can use particle tracking to monitor where things go. And increasingly, we're looking at developing data assimilations, and this is strongly linked to operational forecast, working with the Met Office. So I've picked one physical modelling tool, which is FVCOM. And one of the reasons we quite like this coastal modelling is because it's a finite volume model, which allows us to concentrate detail in the physics around areas of influence. Okay, so we can you can change the scale in the model and focus down, particularly where you're interested in small scale processes, which allows us to, in this case, run a model which covers the Western English Channel and the Celtic Sea, and at the same time allows us to drill down in some detail into Plymouth Sound and up the Tamar Estuary, all in an interconnected model at the same of varying scales. And this allows us, and it's an example of the kind of thing we can do with this. A couple of years ago, we were looking at the impact of wind farms in the Irish Sea. By using FVCOM, we were able to build, within this model domain, nest in at the scale of the individual pylons. So we're actually representing the individual pylons within this regional scale model. Right? And we're looking at what the impacts were on the hydrodynamics. And interestingly, there were two scales of this. One was at a very local scale, where the pylons are actually in the water. You get, unsurprisingly perhaps, enhanced mixing up and down the pylons, which is affecting and weakening the stratification in this part of the Irish Sea. And perhaps the other one is at the whole regional scale domain. This shows the percentage change in the tidal height and tidal range. So we're actually seeing over parts of the domain, anything up to a 1.5–2% change in the tidal height over the, which, if you consider that the tidal ranges in some of these areas can be the order of 2 or 3 meters or even more, but you could, in principle, be you might be actually changing coastal tidal heights by 1 or 2 centimeters, which on the face of it doesn't sound very much until you come close to overtopping a flood defence, when it becomes quite important. Caveat to this is based on a very small subset of model simulations, so it does require further work. Okay. Oh. What the hell's that? I've no idea. You see, that's what happens when you steal your slides from your colleagues. I have no idea. I had absolutely no idea it would do that. Very impressive. Okay, so this then, just moving on into the sort of ecosystem processes. This is a schematic of the model we use at PML, which is at the more complex end of the marine ecosystem models. And it's able to describe the cycling of carbon, nitrogen, phosphorus and silicate through both the pelagic and the benthic systems. It describes primary production, secondary production, as cycling of organic and inorganic material in a coupled system. Okay, so this is one of the more complicated models, and I think there's a sort of adage here: if you put 3 marine ecosystem modelers in a room, you'll end up with about 5 different model descriptions, because nobody will agree with exactly what is the correct description of the marine ecosystem. And as a context of this, we have more recently sort of reconfigured the model so that we can actually change the structure of it at runtime, so we can build models of different complexity, from a very simple sort of single plankton, zooplankton model, the kind of thing that's often used in global climate simulations, through to something that would actually describe ranges of biodiversity. So, well, I suppose the question is, what can we do with this? And there's lots of things we can do with it. We can predict change, we can force these models with climate data. So this is showing shifts in primary production in the Bay of Bengal. We can look at ocean acidification, we can look at the question of deoxygenation, we can look at supply of greenhouse gases from the ocean to the atmosphere. We can explore impacts on aquaculture, fishery, we can look at the impacts of trawling. We can look at eutrophication. Using these kind of particle tracking models, we can look at microplastics, harmful algal blooms, good environmental status. This comes from the Marine Strategy Framework Directive, which is the European policy which is a requirement at a regional scale for UK waters to maintain good environmental status as defined by a range of indicators. Whether, of course, we'll still be doing that in a few years' time is another question. We can also look at things like carbon capture and storage and marine renewables. And particularly, I mean, the kind of things we can then look at these models is, one of the things we've been looking at more recently is, particularly through the Marine Ecosystems Research Programme, is using models and data to move towards indicator selection, which allows us to look at the quantity and quality of ecosystem services, and looking to develop better indicators of the environmental status of UK waters, and particularly around marine conservation zones, so we can support things like the Habitats Directive and the Biodiversity Directive. I mean, this is another example looking at aquaculture. If here in Lyme Bay, so we've got Weymouth here, we've got the River Exe, Plymouth is over here. At the moment there's a very large offshore mussel farm is being developed in this area, and some of these simulations were done specifically looking at the question of where does the mussel seed come from, because the people running the mussel farm out here are putting ropes in the water to try and catch the spat, the juvenile mussels, and while they're doing this and doing this fairly successfully commercially, they don't actually know where the source beds are that release the mussels in the first place. We know there are mussel beds in a number of these large rivers, like the Dart and the Tane and so forth. And I think it's particularly showing here that it's likely, given the location of this mussel farm, that most of the mussel spat they're getting comes from the Exe or the Tane estuary. And moving towards this, we're moving towards developing an integrated model system for decision support, which allows us to take these large-scale hydrodynamic simulations with the ecosystem model and then use this to drive a specific model of shellfish aquaculture so that we can explore the viability of shellfish farming in different parts of the UK under different scenarios. There's a whole range of other things going on. I put this up as the Locate project because I think it sort of segs into the link with the land. As part of the NERC National Capability program, there is a program called Locate, Land Ocean Carbon Transfer, which is led by the National Oceanography Centre, involving us and CEH and BGS. And one of the things Locate is doing is really looking at the issue of quantifying how carbon comes from the land down the rivers and into the ocean. And underpinning this, there's both a very comprehensive fieldwork programme, and they're actually sampling a third of the rivers in the UK. There is also underpinning this a very strong modelling programme, which is actually looking at linking catchment models and developing processes of carbon transfer in the rivers through the estuaries and out into the ocean. And I sort of highlight this because I think this is really, if we are to look at modelling and understanding what's going on in coastal ocean processes, it's crucial that we have high quality information from the land, particularly from the rivers, in order to be able to drive such models. And following on from this, there is, under the auspices of the Joint Weather Climate Research Programme, there is the UK Environmental Prediction Project, which has just begun its second phase through to 2020, is essentially looking to develop a national scale high resolution environmental prediction model, which couples everything together. So you're talking about a coastal ocean model, shell seas model at a scale of about 1 kilometre, with sediments and biogeochemical modelling. We're also looking at wave modelling associated with this, coupled to high resolution atmospheric modelling, so it's being driven by the weather forecasts, and a land surface model. So this is work that's going on in progress, and I think is particularly pertinent to the kind of things we might be thinking around here. I put this up here, I mean, partly just for the gratuitous animation and the pretty pictures of the dart, but we should, the models are frankly, unless you've got the observations, you're never going to get very far with modelling, whether you're trying to either validate them by fitting them to the observations or try and verify them in demonstrating that they reproduce the observed processes. So observing systems, satellite oceanography and collection of socioeconomic data are all vital to this. And it's also a lot of fun playing on a rib in the river. So, I was just sort of thinking about, from a marine perspective, what are some of the challenges we might want to think about in terms of understanding landscapes. And I start with this one, improved monitoring, partly because compared with, I think, a lot of your terrestrial landscapes, the marine coastal waters are very much undersampled. We still don't know, we can see what's going on the surface from the satellite, cloud permitting. What's going on below the surface, even these days we still have fairly sparse knowledge about what the system's doing, even in our own backyard, let alone in the deep ocean. So it's pretty important that we're able to improve the monitoring. I mean, there's a big move into the marine environment towards autonomous vehicles like these gliders, which I suppose in a terrestrial sense they're sort of like underwater drones, is probably the simplest analogy. And what we're interested in doing, one of the things we're looking at is the use of combining models and satellites and forecast systems to provide information to guide these systems to, basically to make these things sort of self-driving and feeding back information into the model forecast systems with a view to improving the confidence in biogeochemical indicators. Okay. But I think in the marine environment, this underpinning monitoring challenge is important if we really want to look at marine landscapes, because we don't have access to the same amount of spatial and temporal data as you do of terrestrial systems. Data assimilation, I think, is also a key. Well, I've gone the wrong way now. Particularly, again, because we're using the sparsity of data, trying to make best use of the data we have in order to be able to get better information on, particularly on forecasting or hindcasting when events occur. This is, for example, deoxygenation events in the bottom waters of the North Sea. And when the oxygen drops below a certain level, you're getting to where these yellows and reds are. These are concentrations of oxygen where potentially you could see significant loss of marine life. This one we've covered before, and I think it's a perennial for all of these, is model skill assessment, it's understanding uncertainty, it's demonstrating the processes in your models work properly, it's demonstrating you can reproduce data, demonstrating you can reproduce processes, it's ensemble simulations. And finally, there's an issue of computational cost, because one of the problems of running marine models is that you have to transport everything. Every variable you have in a marine model is a tracer that goes into your hydrodynamic model and has to be moved around, and this comes at a high computational cost. So there is an issue here that the more complex your marine model becomes, the more computational cost goes up quite markedly. There's a similar issue with scale. If you reduce the scale of have higher resolution models, then the cost of running the models goes up by the square, roughly. So there's a challenge there with computational cost. Finally, some of the work we've been looking at in Plymouth, I put this as an example. It's a challenge of moving from ecologic, economic and social impacts. And we're able to do this sort of bit of taking the IPC assessments and running models. And here we've got some examples. This is the impact on primary production. So carbon fixation in UK shelf seas. There's a difference between 2000 and 2050, and showing the impact of a 30% reduction in river nutrient loads, nitrogen and phosphorus. On the other side, there's a trait-based community size spectrum. So this is showing fish biomass in tonnes. This is in the present day, and if we go into the future, this is the sort of impact of climate change and suggesting what the percentage loss of, mostly in this case, loss of fish biomass would be due to warming. But then there's a challenge here. Mostly at the moment we're using fairly simple economic models, input-output tables, to try and determine direct impacts and so on. And I think there's a challenge here to move this kind of modelling on, and I was particularly interested in sort of the previous talks about the agent-based modelling, as to whether there are some opportunities to be able to move in that kind of direction. I also thought it was quite interesting that the city stuff, the same kind of scaling laws are often very apparent in marine ecology. And again, whether there is some lessons to be learnt by comparing methods there. Again, I just put this up. It's a sort of schematic showing, hopefully usefully showing the role that models can play. And I suppose when I say models, we should really view it in the broadest sense of models, from conceptual, numerical, statistical, however you define a model. We can probably rule out airfix. But the models provide a way of exploring all sorts of parts of the environment, from environment and human health, food, energy. They allow us to explore new ideas through discovery science. They allow us to predict things. They have a very crucial relationship with data and observations, and they allow us to inform a whole variety of social and economic impacts. And the feedback between all of this is very important. Finally, I leave you with a gratuitous animation, if it's going to work. And I put this up just because there's a different way of thinking when we talk about marine seascapes and landscapes. At the risk of sounding cliched, everything is far more fluid. Everything moves around much more quickly over much smaller timescales. There's much stronger connectivity over short timescales in the marine environment. So there isn't a sort of, in terms of thinking about how you address changes out here versus how you address changes on the Rhine Peninsula or the Beer Peninsula up here, in agricultural land use, you're thinking about different timescales and you're thinking about different operations. So you have to bear that in mind. There isn't a sort of one-size-fits-all way of approaching landscapes, and marine landscapes have different timescales and different spatial scales. And again, the same challenge, as I said before, as I alluded to earlier, the impacts on the environment take place out here. The social and economic impacts take place here, and they're not always strongly connected with each other, unless you've got a direct economic dependency, like you're a fisherman or something. Okay, thank you.
Thanks very much. It was very interesting. Pointing out some of the unique features of marine and coastal modelling, but also those links in with land processes as you went through your talk. And a great slide transition, of course. Any questions from the audience? I'm looking into the sun here.
I'm just interested in the decline in production around the northeast of the UK, and do you take that on into seabirds? Do you think about other parts of the food chain?
Well, it will propagate through into seabirds, almost certainly. The models that we're using don't explicitly resolve seabirds at this point, but we have in the past worked with seabird modelers to if you like, another layer of complexity. But when you come back to the sort of human interactions with the marine environment, seabirds are one of the most important issues from a sort of human point of view and their valuation of the marine environment. So it's an important thing to do, but those kind of impacts on fisheries, particularly if it's the smaller fish, are very likely to have significant impacts on seabirds.
Yes, I was struck, Icarus, by the difference between this sort of modelling, which is the modelling I'm more used to myself, coming from the climate community,
Yes.
and the stuff we've been talking about to date, where it still seems to me that in a lot of the sort of biophysical modelling, you might
Yes.
call this, humans are kind of externalities that do different things, choose different pathways.
Yes.
And yet, in a lot of the landscape modelling we're talking about, there was essentially constraints that fed back so strongly that we imagine human behaviour would be changed by the limitation of resource or whatever.
Yeah.
You sort of hinted at this, but are there times in the coastal environment where that's also true, where you can no longer assume that people just do something and carry on doing it forever? I don't know, maybe they run out of fish or whatever. Or maybe
Well, there are some fisheries modelling approaches. I mean, that's the most sophisticated stuff, generally speaking, where people look at, they look at catch, they look at the economic feedbacks, they look at, they tend to use equilibrium models, but they tend to, try and put that in a context of, sometimes in the context of a world trade network. But and then you can look at where people put the energy, whether or not you keep your fishing boats going or whether you take them out of service and so on. So there are some models of feedback like that. There is also, actually, it's a modelling system which I should have referred to in this, and I forgot at the time I was presenting. There's a Australian model system called Atlantis, developed by CISRO, which is specifically designed for this kind of marine spatial planning, and takes a whole ecosystem approach in a box model, but then allows you to do various kind of scenarios, looking at different land use, looking at different fishing, looking at different climate change, and explore. I mean, it's a very complicated beast, and as ever with that type of model, I think it's fair to say it divides the community. But also, I think it has value, if nothing else, as a tool for making people think about how the environment works. And in all of this discussion of uncertainty and things, I don't think we should lose sight of the value of models sometimes, just to make you think about the system, even if you don't entirely trust it.
Right, our final question.
I just wondered if you could say a little more about the kind of aesthetic values, because we saw something this morning, I think, from Natural England, who was talking very much about the value that individuals put on their landscape that they're either walking in or hiking in or whatever. What's the kind of state of play in the coastal stroke marine context?
Well, there is some work is being done on sort of looking at issues of environmental and human health. There's certainly this notion of what they call the blue gym, which is, you know, the idea of the value of the marine environment for people's health and well-being. And as far as I'm aware, some of the studies that have been done around this suggest that actually the benefits of being in a marine environment outweigh those of being in a healthy terrestrial environment. You know, being in the national park, being in the forest. You know, but there are parts of work. I mean, we've done a little bits being done in Plymouth, and there's more work being done in Exeter along these lines. I don't know too much more about it, but hopefully that at least helps a little bit to answer your question.
Great. Well, thanks very much
Okay.
for your presentation.